Welcome everyone. Welcome. Uh, in today's session, we are going to discuss and work on classification tree algorithm. We'll start off with some basic concepts of classification tree algorithm, and then we'll get into building a classification tree model using Python. So in the last session, we saw application of classification tree in retail banking, and at length, we discussed a retail banking case study. The challenges in building a classification tree model, as you would have gone through the case study, you would have realized some of the challenges while building the model are: how do I identify which variable to be considered for splitting purpose? For example, as we have this tree, at the root node, which variable should I consider to split the root node into child nodes? That is called splitting criteria. There are many predictor variables, independent variables which are available. But of the many, which is the one? Because a node can be split only using one variable. You cannot split a node with multiple variables. So of the many variables, which is the most important variable to be considered? That is the first challenge, identifying the splitting criteria. So you require some logic by which you can prioritize and say this is the most important variable at this particular node level. Second is, if you have identified the variable based on which you have to split, how many child node you should have from the parent node. For example, when you are taking inactivity period, length of inactivity for splitting the variable as shown in the diagram again in the classification tree, I could have split less than 12 months and greater than 12 months, or I could have split saying less than 12 months, 12 to 18, greater than 18. Again, identifying the optimal cut points, what should be those ranges, is second important challenge. We as human being probably would do trial and error and then say, okay, these should be the cutoff points, and based on that we create the child nodes, or we would have gone through some business logic and decided the range. However, when you're giving it to algorithm has to automatically identify the optimal. So this is the second important challenge: how many child nodes and what should be the cutting criteria, what should be the range. If it is a gender kind of a variable, then automatically male female, but the challenge is more predominant when it is a continuous variable. Once you have a root node split into child nodes, there may be a requirement that the child node should be again split further. So which means you have to repeat the step 1 and 2. Now, how many times you should split the child node? Once you have root node, you got child. This child you are again going to split. It is going to give you further child nodes. The child nodes further can be further split. How many iterations of this splitting of nodes should happen? So there is something called as stopping criteria. There has to be some logical point where you may want to say that there is no further benefit I'm going to get by further splitting the node into child. So the algorithm has to also decide how many levels of splitting has to be done. As a human, intelligence, if we would have done, we would have considered all of that and built the tree. However, this entire human intelligence has to be imbibed in a algorithm, that is the classification tree algorithm, and the classification tree algorithm provides all of these features: feature of splitting criteria, how many child nodes should come from a given parent node, and how many levels you should go, what should be the stopping criteria. So based on how you identify the variable which is the most important variable for splitting at a given node level, there are three main algorithms. There are three popular algorithms, and those popular algorithms are CHAID, CART, C5.0. At a broad level, these three algorithms make use of three different mathematical formulae to arrive at the best variable. We'll discuss that in short while, but at this point of time, you just understand you have got three different algorithms in classification tree technique, and these algorithms make use of different ways of computation to find the best variable. Then once you split a given node, certain algorithms split a given parent node only into child nodes, and there are certain algorithms which split a given parent node into more than two or more than two child nodes. So CHAID, which is a technique which makes use of a chi-square statistics. Chi-square is a test of independence. CHAID technique makes use of chi-square statistics. That technique can split a given parent node into two or more child nodes. Whereas the other two techniques, CART, which makes use of something called as Gini gain, and C5.0, which makes use of a concept of anthropic gain. These two techniques split a given node into two child nodes only. We are at very high level, but you just try to keep understanding high level concepts first, and then we will get into lower level, more details, mathematical calculations, and building the classification tree model using Python. So I have explained the first two. A classification tree technique helps you identify the right splitting criteria. A classification tree technique has got algorithm by which it decides two-way split or multi-way split. Then stopping, how many iterations it should have. So classification tree techniques has got parameters like max depth, by which you can say how many levels you should go, or there are parameters by which you can say in a given node I should have at least these many minimum number of records. If the terminal node does not have these many minimum number of records, that cannot become a terminal node, which means you have to go one level above or two level above. Okay. And there can be also criteria that a node should have certain minimum number of records, only then it will be further split. I can say a criteria: if a node has less than 1000 records, that node cannot be further split, which means the moment a node, as the splitting keeps happening, moment a node has less than 1000 records, that node will automatically become terminal node. So you can have various stopping criteria, like how many levels of split you want, what should be the minimum number of records in a terminal node, what should be the minimum number of records in a node, only then it will be split, otherwise it will not be further split. So those are stopping criteria. And again, there are certain concepts some of the algorithms in classification tree provide you, that is called as pruning. Pruning is a concept where you allow the tree to grow very large, which means you have a very relaxed stopping criteria. You do not have a stringent stopping criteria. I can have a very relaxed stopping criteria saying that the tree to grow till each terminal node has one record, and the minimum number of records in a node to further split is say 2. I can have such a very lenient stopping criteria. In that case, the number of splits and the levels will be too many. The depth of the tree will be too long. However, when you have such a lenient stopping criteria, you will not get an optimal model. So there is a concept called pruning. In a pruning, what happens is you allow the tree to grow tall. After the tree has grown, you identify the nodes which are actually not making any sense, and then you start pruning it. The other way of looking at is, the simple concept of pruning is, when you go to a garden and you would have seen that in the garden there are many trees and plants, and on a periodic basis the gardener who maintains the garden keeps trimming the branches of certain trees and plants which are grown in direction which probably interfere with the people walking in the garden, who come to visit the garden and so forth. So unwanted branches are periodically pruned off. So similarly, the classification tree technique allows you to give a very lenient stopping criteria which will result into many unwanted branches. Those unwanted branches you can then prune off, you can then cut them. Okay, so that is the concept of pruning. So at a very high level, I've explained the challenges which we face while building the model, classification tree model. The challenges are: how do I identify the right variable to split? How many child nodes can come out of a given parent? How many iterations I need to do? Where to stop? So these are my challenges, and these challenges are very well addressed by classification tree technique, and all of that are handled. There are three predominant techniques: CHAID, CART, C5.0. Now we'll discuss one of the technique in depth. What is CHAID, what is CART, and what is C5.0 at a definition level I'll explain, and then completely detail out the CART technique. So here I've got this entire presentation of mine. Let me get into full screen mode. Okay. What all things we are going to learn? We are going to go into detail for the CART technique. The other two techniques at a very broad overview I am going to give here. Here I have mentioned C4.5 technique. C4.5, the advanced version is called C5.0. And there are many concepts which we'll learn as we get into Python programming. So let's formally define classification. What is classification? When we are building a classification tree model, classification tree model, as you know, is a supervised machine learning technique. In that, the classification is actually a two-step process. Step one is profiling. Profiling means explaining the characteristics of a class. As we saw in the case study in last session, we had overall campaign data, and that data was at the root level of the tree, and that root level data was split into childs and then further split till you got the terminal node. The profiling characteristics of any terminal node can be identified by navigating back. For example, if I navigate backwards, if I navigate backward from this terminal node, 1 minute, yeah. If I navigate backward from this terminal node, at each level I will come to know what was the criteria by which the above parent node was split. And as I keep noting down the criteria by which the parent node was split, those criteria actually becomes the profiling characteristics of the terminal node. If I know these profiling characteristics, I can use that for my future campaigns. Now, how do I use that for my future campaigns? Once I know the profiling characteristics, once I know the profiling characteristics on other data set which is available for campaigning, or the newer data set which comes into my system as each day passes, on that data I can apply the profiling characteristics and predict the class of that record. So when I am applying the profiling characteristics on the newer data set, remember, you do not have the output. You are actually predicting. The word prediction is more important. On newer records, when you apply, you do not have the output. You are applying the profiling characteristics, the learning of the classification tree model. You are applying on the newer records and predicting their class. And by predicting the class, you then take appropriate deployment strategy so that you maximize your return on investment or you minimize your risk. How to do all that ROI calculations were detailed in our classification tree case study. What are the benefits? This technique is very simple, intuitive. You get a visual output. You do not require lots of data preparation. In a classification tree technique, you don't require lots of data preparations. You do not need to bother about outlier treatment. Missing can be easily handled by creating a category saying missing. So these are the benefits of a classification tree technique. Now coming to this classification tree, what are the three main algorithms? The three main algorithms as we discussed are CHAID, CART and C5.0. C5.0 was earlier called C4.5 and before that it was called ID3. Okay, there is improvisation in the algorithm logic. CHAID. The full form of CHAID is chi-squared automatic interaction detector. The first term is chi-squared. As the term chi-squared suggests, it makes use of the chi-square statistics in the algorithm. The chi-square statistics is a test of association. It is a test of independence. And based on the chi-square statistics, you actually compute the significance of all your independent variable vis-a-vis the dependent variable. You will get the significance for all the variables, that is p-value. The variable which is the most important at the given node level, the variable which is the most important based on the chi-square test is the most significant, and that variable would be actually used for breaking the node, for splitting the node into child nodes. and because it uses the chi-square, it is called as chi-squared automatic interaction detector. Now, why automatic interaction? The technique involves creating of contingency table, that is table between the dependent and independent variable. The contingency table is what is that required for doing the chi-square calculation. So automatic cross tabs between the dependent and the independent variable gets created. Okay, and that's the reason automatic interaction. Okay, this it does all of that automatically. In certain implementation, the continuous variables are automatically handled by the algorithm. However, there are certain implementations, for example in R, continuous variables are not automatically converted to categorical. In that case, we have to convert the continuous variable into buckets before we call the classification tree algorithm using CHAID. So that is chi-squared. The second technique is CART, and CART is the technique which we are going to implement in Python. CART makes use of an algorithm which is called Gini gain. Now, what is Gini gain? Gini, the dictionary meaning is measure of impurity. There are certain mathematical formula which classification and regression tree, that is CART technique, use, and that algorithm makes use of Gini gain. How much of impurity is reduced? Gini gain is how much impurity is reduced. Gini is impurity. Gini gain is reduction in impurity. The third technique, C5.0, makes use of a concept of entropy. Entropy concept comes from thermodynamics. It makes use of that entropy formula. The entropy formula which is in thermodynamics is applied on data, and here we call it information gain, also called as entropy gain. So based on how much is the information gain, it identifies which variable is the most significant. The variable which gives the highest information gain is the most significant. As I mentioned, we will discuss CART technique at length. So let's get into the CART technique and let's see what is the Gini gain. First and foremost, by now you might have started thinking, okay, what is the formula? How do I do the calculation? So to quench your this thirst for knowing how we do it, let's get into CART and let's see the calculation. This slide shows you the formulae of calculating Gini, the formulae for calculating Gini gain. The first bullet point is the most important, which I want you to understand, and then we will see calculation using data. Gini is called as measure of impurity. How impure is data? Some way of quantifying that, and one of the approach is using Gini. Assume you have a data set in which 100% of observation belongs to, say, responder class. So let's assume we are taking a business problem and we are taking the same banking business problem of dormant account win back and no win back. So assume you have got a data where all records are of win back, the customers who responded to your campaign. If I ask you how pure or how impure is this data, because all customers belong to win back segment based on the win back or no win back segment, because all of them belongs to win back, I would say that data is 100% pure, because everyone belongs to a given segment. If I have a data where 90% of observations are win back and 10% are no win back, in that case I may say the data has some impurity, because the data is not completely homogeneous. There is certain level of heterogeneity because it is a mixture of two classes. If I say the data has got 75% win back and 25% no win back, and compare it with a data having 90% win back and 10% no win back. In this case, 75:25 versus 90:10, I would say the data having 75:25 composition of the two classes is more impure compared to the data having 90:10 distribution. Now, let us compare two data sets. One of the data set has 90% responder. So let me say 90, and let me also have the symbol of percentage. 90% responder, or you can say win back. I use now the term responder, or let me, okay, responder. 10% non-responder. These are my two classes, responder and non-responder. And there is another data set which has got 10% responder and 90% non-responder. Sorry, yeah, 90% non-responders, 10% responders. Now, if I ask you which data is more pure or which data is more impure, this is my data set 1 and data set 2. Think over it and tell me which data, D1 or D2, which is more pure and which is more impure. Both the data set D1 and D2 are equally pure or equally impure. There is no difference in their impurity level. The point I am trying to drive is the purity or the impurity is measured on the composition of the classes. The Gini formula, as you can see here, is 1 minus proportion of each class at given node level square of that term. 1 minus summation of the proportion of each class square at given node level. So if I have to compute the Gini for node D1, the formula in this case as per the Gini is 1 minus, and then what is saying, proportion of each class. The first class responder is 0.9 and we have to take the square, 0.9 square. The second one is 0.1, so here it will become 0.1 square. Likewise, if we have to compute the Gini of the second node, D2, data set 2, it will be 1 minus 0.1 square plus 0.9 square. So from a Gini calculation point of view, they are equally impure. So first we have understood Gini. Now let's try to understand the Gini calculation when the proportion of the two classes is 100% responder and 0% non-responder. What will be the Gini in this case? It will be 1 minus 1 square plus 0 square, and it will be 1 minus 1 square plus 0 square, it will be 0. As you can see, it is completely pure. The Gini value is, the measure of impurity is coming 0. In a two-class system, the maximum impurity can be in a scenario where both the classes are 50:50. When responder, non-responder, true, false, yes, no, defaulter, no defaulter, both the classes are in same proportion. In this case, the Gini will be 1 minus 0.5 the whole square plus 0.5 the whole square, and this will turn out to be 0.5. The highest level of impurity in a two-class system is 0.5, which means both of them are in equal proportions. The formula can be extended from a 2-class to 3-class to 4-class. The formula remains same: 1 minus proportion of each class the whole squared. So you have to just keep seeing what is the proportion, square them, do summation, subtract it from 1, and that becomes the Gini. So first we have understood the Gini, and we have also seen that when the data is 100% pure, when all records belong to only one segment, the level of value of Gini is 0, which means no impurity. And when both of them are 50:50, the maximum value of Gini impurity can become 0.5. So the range of Gini is, in a two-class system, is 0 to 0.5. This is the range. So this is the first point. Now, how this Gini measure of impurity is used to find out the best variable. So what will happen is, you will have a root node. You will have a root node, and this root node is actually a mixture of your classes, and we'll just have two classes: response, no response. So this root node will have certain Gini value depending upon what is the proportion of your response and no response. So here, this is your Gini of the root. Or probably what I'll also do is, I'll remove this RN and type here also root, because otherwise you will have some confusion. So this is my root node. So here I have computed the Gini of the root. I have to find out which variable is important. So let's just assume there is some variable XYZ, and based on that XYZ, this data is split into two child. So I can have, hypothetical is what I'm doing as of now. You will have a Gini of child 1, then you will have a Gini of child 2. Both the nodes you have to compute Gini. How you do all of that, we'll do in a small simple example, and then you have to compute the Gini of these two nodes taken together. How do you compute the Gini of these two nodes taken together? Using a weighted average. You have to assign weights to child 1 and the weights to child 2. The way the weights are assigned depends upon how many observations are there in the given child divided by total number of observations. If there are more observations in, say, child 1, it will get higher weightage. and because there are less observation in child 2, it will get less weightage, and that's how you compute Gini of the two child taken together. And the difference between the root node and the split node Gini is actually called Gini gain. So this is the entire theoretical aspect. With theoretical aspect, probably you may not have understood completely. So let's take a practical aspect, wherein we will have a small data set. On that small data set, let's do calculations and find out Gini gain. Okay, let's do a practical calculation. Here is a small data set. We are just having 10 observations in this data set. 3 variables: gender, occupation, age. These are my independent variables. Target, that is my dependent variable. In target, you can see the values are 1 and 0. 1, let's say, is win back. 1 is win back, that is responder, and zeros are non-responders. I want to find Gini of the root node, step 1. And I want to find out this root node should be split based on which variable. Should I split based on gender or occupation or age? My objective is to split the root node such that I have more homogeneous data, at least in one child node. Okay, so that is my objective. So I have to find out which variable is the best. And the definition for best variable in the CHAID technique is the variable which gives you highest Gini gain. So if that is the definition of how the algorithm is implemented, then I need to know how I have to compute Gini gain. When you are going to use a Python program for building classification tree, or if you are going to use a R algorithm for classification tree, manually you are not going to do the calculations which I am going to exhibit. All those calculations will be done automatically by the system. The reason why we are understanding the manual method of calculation is to better appreciate the technique. That is the objective. So let's take the example and first compute the Gini of the root node, with the assumption that the root node will be split by gender variable. So let's focus on the root node. Overall number of observations are 10. Now in the root node, how many responders are there? There are 4. So here I have given only 2 information. Total number of observations are 10. The number of responders are 4. Obviously, the number of non-responders is equal to 10 minus 4 equal to 6. So if I have to find out the Gini of the root node, the formula will be 1 minus proportion of each class square, summation. My responder class proportion is 4 by 10. So I have to take the square of that, 4 by 10, the whole square. The non-responder class proportion is 6 by 10. I have to take the square. Summation of 4 by 10, the whole square, plus 6 by 10, the whole square. Subtract it from 1. I get Gini 0.48. So Gini of my root node is 0.48. Now I am assuming that the root node is split by gender. Now in gender we have got male, female, 2 categories. In male, how many observations? 6 observations. How many responders in male? 3. In female, how many observations? 4. How many responders in female? 1. So let us compute Gini of male node. Gini of male node will be 1 minus 3 by 6 the whole square plus 3 by 6 the whole square. Now, why I'm taking 3 by 6 the whole square two times? The first time I'm taking it for responder category. The second time I'm taking the proportion of non-responder category, and it happens to be both the classes proportion is 3 by 6, 3 by 6, that is 0.5, 0.5. So the Gini of the male node turns out to be 0.5. What is the Gini of the female node? The Gini of the female node is 1 minus 1 by 4 the whole square. 1 by 4 the whole square is proportion of responders plus 3 by 4 the whole square, which is the proportion of non-responder, and that Gini turns out to be 0.375. We have to now compute the Gini of this composite, both the child nodes taken together. We have to compute the Gini. So Gini of the split two childs taken together will be calculated by giving proportional weights. Now, how much weightage I should give to this? I will have to give it a weightage which is 6 by 10. Why 6 by 10? Because it has got 6 observations out of the 10 in the parent node. And the weightage I will have to give this Gini will be 4 by 10 because it has got 4 observations out of the 10. So here is the calculation. 6 by 10 times the Gini of male plus 4 by 10 times the Gini of female, that is the Gini of the split node. What is gain? You have to subtract the split node Gini from the root node Gini, that is 0.48 minus 0.45, and that is the gain. So this is the calculation of Gini gain. The value 0.03 in absolute terms does not have any meaning. It has meaning only in relative terms. How it has got meaning in relative terms? This Gini gain which we have calculated for gender has to be compared with the Gini gain that we will get for occupation. It will have to be compared with Gini gain that we will get for age, and based on that relative comparison we'll have to conclude whether gender, occupation or age, which variable is the strongest predictor variable at the given node level. Let us now see the calculation for occupation. In occupation, we have got two categories: salaried, self-employed. There are 5 observations of salaried and 5 observations of self-employed. So here I have noted down 5 for salaried and 5 for self-employed. Again, how many responders are there in salaried? If you see, there are 2 responders in salaried and 2 in non-salaried, that is self-employed. So I have noted down how many responders. If we apply the Gini gain calculation, root node will remain same. It is not going to change. For salaried, it will be 1 minus 2 by 5 the whole square plus 3 by 5 the whole square. It is 0.548. Similarly, for self-employed, it comes out to be 0.48. The weighted average will also come out to be 0.48. Gain, there is no gain. See, it's very logical. Here the data was 10:4. Here the data is 5:2. You just double it, it becomes 10:4. Which means by splitting based on salaried or self-employed category, I am nowhere concentrating responders in one side and non-responders on other side. I have the proportion distribution of responder and non-responder same as that was in parent node. So this variable is of no use. Now come to the third variable, age. Now age, as you can see here, does not have got two categories. It has got continuous integer values 22, 23, 24, 25, 26. Now how does continuous variable get handled? First I'm going to give you a theoretical way for calculation purpose. Let us assume this entire data is split as less than equal to 22 and greater than 22. So less than equal to 22 I call left node, greater than 22 I call it right node. So I got my two childs. Can I compute my Gini gain? Yes, I can compute. Then I will assume the data is split at 23, less than equal to 23, greater than 23. Once again I get left, right, two childs I can compute. Note, why two child? Gini gain CHAID algorithm splits a given node only in two child. It does not have multi-way split. It can split a given node only in two. That's the reason each time we are splitting a root node, we are showing only two child. CHAID algorithm has multi-way split. We are in CHAID algorithm. So here what I've done is assuming the data will be split as less than equal to 22, less than equal to 23, less than equal to 24, less than equal to 25. For each of them, I am calculating the gain. Now based on the CHART algorithm, the variable which gives you highest Gini gain at a given node level, that is the best variable. Now here my Gini gain values are 0, 0.0, 0.01, 0.03, 0.08. For occupation, it is 0.0, and for gender, it is 0.03. Of all the Gini gains, the maximum gain is 0.08. So we will consider age variable for splitting, and the way it will happen is root node being split on age less than equal to 25 and greater than 25. So here one side I have less than equal to 25, other side I have greater than 25, and that will be my first level split. Once you have got the two child nodes, if I have to further find which variable is the best variable to split further, once again I'll have to do comparison for gender, occupation, age. A variable which has come can again come in the next iteration also. Here the data is small, but just think you have got 1 million records and the age is not restricted to 21, 22, 23, 24, 25, 26. Age has got a range from 18 to say 100. And the first level of split comes as age less than 40. Now within 40, age could have further split 35. Above 40, it could have further split less than 60. So a given variable can again come for splitting. This is the point one that I want to inform. A variable can repeat. The second important thing is it was very easy for me to demonstrate it. Less than equal to 22, 23, 24, 25. However, if you have a variable say balance, the balance maintained by customer in the account, the balance maintained by customer in an account is not 1 rupee, 2 rupee, 3 rupee. It is not rounded amount. The balance maintained by customer is continuous number. One customer can have a balance of 0 rupees. The other customer can have a balance of 0 rupees. Oh, sorry, 0.01 rupees. That is 1 paise. One can have 1 lakh rupees. The other customer can have 1 lakh 1 paise. So in that case, when you have a large data set and the continuous variable can take any continuous number, you cannot have the algorithm trying all possible combination 1 paise, 2 paise, 3 paise, 4 paise, less than 1 paise, greater than 1 paise, less than 2 paise, greater than 2 paise. Algorithm cannot have doing that. So there has to be some optimization algorithms. I'm just trying to show how I would have done the optimization. Assume this is the range of the continuous variable. Okay, so this is my range of the continuous variable, this some distribution. I would have taken the 50th percentile, and I would have taken the first quartile and the third quartile values. So I will split the data. I'm just giving my logical approach of how I would do optimization for continuous variable to find optimal split point with very few iterations. So what I will do is the continuous variable, I will find out what is Q1, Q2, Q3. And with Q1, Q2, Q3 less than, greater than, I create 3 calculations of Gini gain and see where I get better Gini gain. Assuming the Gini gain for Q1 is the best compared to Q2 and Q3. In that case, it is very clear the optimal split is in this half. So which means I have narrowed down 50 percentage. Then probably I will do 10 percentile and say 35 percentile. Once again, I'll compare 10 percentile with 35 percentile. And if 10 percentile is better than 35 percentile, which means the optimal split is now in this much range only. This approach I would have taken to quickly find in some 5 iterations where is the optimal split criteria for a continuous variable. What is the actual optimization algorithm implemented in CART logic? I really don't know. What I'm trying to convey is in CART technique, continuous variables are automatically handled and it will automatically find the best splitting point for a continuous variable. The entire logic is implemented. We are not supposed to do the Gini calculations manually when we are going to run the CART algorithm using Python, or we are going to run CART algorithm using R or any other machine learning tool. Our objective is to, at a very high level, understand when I'm using a CART algorithm, the variable which is best is identified using a calculation which is called Gini gain. And what is the calculation of Gini gain is what I have demonstrated. Very important for us to know how to go about doing calculation of Gini gain. So I have a problem statement for you. This is a classification tree, root node split into 2 child. The problem is you have to calculate Gini of the root node, Gini of the left child, Gini of the right child, find out what is the weighted average of the child nodes, and then compute Gini gain. So I'll keep this screen for a while so you can focus on the screen and do the calculations. Okay. Those who are watching the video, the answer to this is 0.007. You are all James Bond. Let us now apply the CART technique on Iris dataset. Iris is a dataset which is available inbuilt in Python. It is a balanced dataset. CART technique is typically applied on balanced dataset. When you have unbalanced dataset, you have to do some oversampling, undersampling, or combination of over and undersampling to make that data somewhat balanced. Now, what is balanced and unbalanced? When the proportion of the classes in your dataset are more or less equal, we call that dataset as balanced. I repeat, when the proportion of your labeled class column in your dataset is more or less equal in proportion, we call it balanced. For example, iris dataset, it is a famous dataset which is available, and it was collected by Fisher, a well-known statistician, and it has got data of iris flower which has got three species. The three species are setosa, versicolor, and virginica, and the dataset has got 150 observation, 50 observation for each of the above mentioned species, that is setosa, virginica, versicolor. And because there are 50 observations, which means one third, one third, one third, proportion is same, the dataset is called balanced. And there are four attributes. Those are sepal length, sepal width, petal length, and petal width. The flower is as shown in the image here. What we have to do is, we have to build a classification tree model wherein based on the sepal length and sepal width, petal length and petal width, these four attributes, we have to classify whether the species belongs to setosa, versicolor, or virginica. That's our problem statement. It may appear too trivial a problem statement, but it's still a challenging problem statement. And for your information, based on this simple data set of 150 observation, Fisher developed a machine learning modeling technique by the name linear discriminant model. We are using classification tree algorithm, but Fisher developed a technique using this 150 odd records. So we'll now get into our Python Jupyter Notebook environment, where we will run the codes to build classification tree model on the iris dataset. So here is my Jupyter Notebook. I require NumPy. I require a package Py.plus. If you don't have the Py.plus, then on your Anaconda prompt, you can run this syntax to install that. I require IO because as we build the classification tree model, we will have to create an image of the classification tree and save it. For that, I require IO, input output package, matplotlib inline to show the charts and graph in your Jupyter Notebook. This is the syntax matplotlib online inline which we have to execute. So let me import the packages. In sklearn datasets, we have got the iris dataset available. So we'll load this package, and from that we'll take the iris dataset. When we see this dataset in Python, we will not be able to see it nicely in a data frame format. So I'll just show you what are the features. There are four columns, attributes, as I mentioned, sepal length, sepal width, petal length, petal width. And we have got a column which has three species: Setosa, versicolor, virginica. The data set has 150 observations, and the values of these three species are coded as 0 is coded for Setosa, 1 has been coded for versicolor, and 2 has been coded for virginica. Let me just show you the type. The iris.data is of type n dimension array. This iris.data, which is n dimension array, you have this values. The first 4 values corresponds to the first record. The second set of 4 values correspond to the second record, and the values for the first 4 records are in this sequence. The first 4 records belong to sepal length, sepal width, petal length, petal width. And what is the target? Target value for that is 0. 0 means Setosa. So as such, I mentioned you the way the data set is in Python will not be able to visualize it nicely. As such, I am describing each of them very slowly. So we'll take the iris data, which is the values for the 4 attributes as we discussed: the Setosa, versicolor, virginica, the sepal length, the sepal width, petal length, and petal width, the 4 attributes. We will capture that as x. Why x? Because x, we know x is typically used as a notation for independent variables. So x is the notation. The target is my y. So let me capture that as y. So x and y. Whenever we build models, I have not executed x. Let me execute that. Whenever we build a model, we typically split the data into training and testing. On training set, we build the model. We use the model by applying it on a testing set to see how good is the model. If we get a good accuracy on the testing set, we then go ahead and deploy the model for business purpose. So I need to split this 150 observations into train test. There is a package called train test split. So let me load that package, and using that package, I am going to split the iris dataset where the attributes I captured in X, the target I have captured in Y. I'm going to split this into 2 datasets. Test dataset will be 50 observations. Training will have the remaining 100. Random state is just an attribute to set random initial point, so that what it means is if I run the code next time again, the subsequent steps will give me the same output. Because when we are doing training and testing, the split of data happens randomly. If I don't use this random state, the training and testing set, each time I execute this code, I'll get a different data set, but I want same data set. Because I have set random state 42, and if you on your computer also set the random state as 42, you can give any value here. If you also set the 42, my output and your output is going to match. Let me just print the shape of train. So train has now got 100 rows, 4 columns. and Y train has got 100 rows because it is got only one target column value. And test has got 50 observations and 4 columns and 50 values for the target. So I got my train test. Let me see the distribution of the 3 species on the training set. So there is a function binary count. I'm just trying to show the distribution. So the distribution, it says that in this data set, target value 0 stands for Setosa. There are 31 observations of Setosa. One is Virginica. Now, how do I remember that one is Virginica? Sorry, one is versicolor. How do I remember that? Based on alphabetical order. 0, 1, 2. So these are alphabetical, V, E and V, I. So 1 will be for versicolor and 2 is for Virginica. So we have got 31 observations of Setosa, 35 of versicolor and 34 of Virginica in the training set. More or less the proportion is same. That's why it is balanced data set. To build the model, we require a decision tree classifier object. So I require a package where I'm going to import tree from sklearn package. From tree, we have a function called decision tree classifier. I can have many parameters which I can set. However, I am setting only one parameter saying max depth equal to true. That is, I am saying build a classification tree model having only 2 levels. What are other parameters which I can set? If I want to know somewhere around this bracket, my cursor is blinking. I just press Shift Tab button and it is going to give me the help documentation. So as you can see, the help documentation, it says the first thing is criteria Gini. So it is making use of Gini logic, Gini gain logic, which we just discussed for identifying the splitting variable. Then there are many other parameters which I can set. But for now, I'm saying the data set is small, only 150 observation. From that, we took only 100 observations in training. So I am saying, okay, make a tree having only 2 levels. So first we have to create the classifier object. Having created the classifier object, we have to fit the model on training set. So we have to call a function fit. To the fit function, we have to pass independent variables. My independent variables is x underscore train. It has got the 4 independent variables. And I have to pass dependent variable, which is y underscore train. So I have to pass these two to the model where we declare this x underscore train and y underscore train. This is where we got this x train, y train when we had split our xy. Xy is the overall data set. Using train test split, we had got this x train and y train. So I'm going to fit the model on the training set. Now the model is built. Where is the model? The model is in this object CLF. I have to visualize this model. To visualize this model, there is a certain lengthy code which I've got here where I'm making use of export graphviz, miscellaneous package, pyplot, and so forth. The latest version of decision tree classifier supports a function for plotting the decision tree model which has been built. So let me first try that function If that works, then great, else I'll run this piece of code. Let me type that syntax. Okay, this is the code which has executed. So there is a plot tree function which has been added. This function is giving the output. As such, I use this plot tree function, and I'm not going to use this complicated code which was to be written in earlier version of classification tree, decision tree package. So thanks to this plot tree function, I have executed this, and I've got the output. Let's just try interpreting this output. To interpret the output and have this entire output on one screen, let me reduce my font size. Still it has not come. Okay, yeah, here is the output. So what you can see is the entire 100 observations are at the top. Focus on the cursor, mouse cursor, and the values 31, 35, 34. 31 is number of Setosa observations, 35 is number of versicolor observations, and 34 is Virginica. Which species is dominating here? Versicolor. Because versicolor is the majority class, you see versicolor class being written here. And Gini of this node is 0.666. If it would be 2 class, the maximum value of Gini can be 0.5. But if it is 3 class, then you can have 1 minus 1/3 the whole square plus 1/3 the whole square plus 1/3 the whole square. So that can become the maximum value. This data is split on basis of petal width less than equal to 175. All observations of petal width less than 175 is on the right node. On the left node, all observations where petal width is more than 1.75 centimeter is on the left node. And when you split the data by petal width greater than 175, you can see all Setosa observations have come on the left. Just imagine you have this data in front of you where you have the attributes and the target variable, and then you have to find out by which attribute can you split it. It would have become too difficult because there are 4 columns. It would have been difficult for us to find out which variable we should be using. The classification tree algorithm using the Gini gain has optimally find out that if you split based on petal width, you will be able to accurately identify the Setosa species, because petal width greater than 1.75, the species will be Setosa. Now, in this node, you do not have Setosa, you have versicolor and Virginica. Here you have all Setosa, that's why the class is Setosa. This right node is further split. This time around, which variable to be used? Oh, sorry, I described wrong here. Petal width less than 1.75 is used at this level. Petal length less than equal to 2.45 was used at the top. My mistake, apologies. The first criteria considered is petal length less than equal to 2.45. All observations where less than equal to 2.45 are gone on the left hand side, and the remaining are on the right hand side. Once again, the next variable that is being used is petal width. Petal width less than equal to 1.75, those observations are going on the left hand side and remaining on the right hand side. So here, when you see the terminal nodes which are marked in orange, green and purple, in orange 100% accurately Setosa has been identified, but in green if you see, there are 34 versicolor, 4 Virginica cases, which means when I split the data based on petal length and petal width combination, I am able to accurately identify versicolor and virginica to a large extent. However, there are certain observations which are wrongly getting classified, because this node, majority of them, in the green node, majority of them are versicolor, but a few virginica species has also come. So what is the accuracy of my model? If I have to find out, what I'll have to do is, I'll have to use the model which we built above to predict on X test. Let me increase the font size once again. Yeah, I'll have to use the model on my test data set and predict the classes. The predicted values I'm capturing here as predict Y test, and this predicted values I have to compare with the actual. So Y test actual, compare it with predicted Y test and come up with the accuracy. If I say the actual is 1, I predict 1. If actual is 0, I predict 0. If actual is 2, I predict 2. That is accurate. But if actual is 2, I predict 1. That is wrong prediction. So how many cases I have wrongly predicted out of the total is my error, and how many cases I have correctly predicted is my accuracy. There is a sklearn metrics package in which you have got a function accuracy score. In accuracy score, you have to give the actual values, you have to give the predicted values. It will give you the score. So when I see the score, I find I have done 98% correct prediction. If you want to show this in a contingency table format or a confusion matrix format, confusion matrix is another name of contingency table, or simply put cross tab format, I get this cross tab. What this cross tab is showing you, there are, in the test data, there was 19 observations of setosa. All of them has been accurately predicted. There were 15 observations of versicolor. All of them has been correctly predicted. There were 16 observations of virginica in the test data, but one observation got predicted as versicolor. Now, how do I know the order? Once again, as I mentioned, it is in alphabetical order: setosa, versicolor, virginica. So if I see, diagonal values are all correct. So 19 plus 15 plus 15, these are correct predictions. What are the total number of observations? Total number of observations are 50 in the test data set. So I can compute the accuracy score like this also, 0.98, which we already got 0.98. Now, if I do not have this classification tree model, in that case, what would have been my accuracy? If I do not have the classification tree model, I randomly predict the species. There are 3 species. If I randomly predict, my accuracy would be 1/3. Now, why 1/3? Let us understand this from a multiple choice questionnaire examination. Assume you are attending a MCQ test where there are 4 options. You are not well prepared for the multiple choice questionnaire. You randomly tick any one of the option for each of the questions. There are 4 options. Randomly you are selecting one option for each of the questions. What is the probability of you being correct? Because there are 4 options, you are randomly selected, your probability of being correct is 1/4. So similarly, there are 3 species. if you randomly predict the class, your accuracy would be 1/3, that is 0.33%. However, by building a model using the classification tree algorithm, we have increased the accuracy to 0.98. So this is where a CART technique is beneficial when you have a balanced data set to identify the profiling characteristics of your classes accurately. To predict the output, classification tree technique does a good job, and you can see a drastic improvement in the accuracy using a classification tree model vis-a-vis compared to random prediction. In this case, we have increased the accuracy from 0.3 to 0.98. This was an application of CART technique on balanced dataset. In our upcoming session, we will discuss application of classification tree technique on unbalanced dataset. Thank you. Bye bye. See you in the upcoming session.